and how to use them. Now on the other side, we have a software developer who, if he thinks about cryptography, he thinks about it more in terms of private data and passwords and data encryption. So more like high-level concepts and not really the down-to-the-wire stuff like algorithms. So a software developer is not really a crypto expert. But when you look at how the developer is supposed to use these APIs, then you notice that he would have to be one to correctly use it. For an example, let's imagine you're a developer who wants to implement a file encryption in Java. Currently, with a standard API, you would have to do two things. At first, you would have to create a cryptographic key by means of this key generator API here. You instantiate it by a call to get instance, then you pass the encryption algorithm AES, then you set the key size by a call to init, and then finally you can generate the actual key by a call to generate key here. Now this is the first step. Now you've created the cryptographic key. Now comes the second step, which is the actual encryption using the cipher API here. Again, you instantiate the object by a call to get instance, and you pass this encryption algorithm here. Then you call in an init method. This is sort of a common pattern with these APIs, that you have a get instance call, then an init call, and then a call to finalize the operation. So here in this init call, you again pass some configuration parameter like you want to encrypt and not decrypt. Here's the key, and then some initialization vector. And then finally, in the sixth call here, you can perform your actual encryption on your file data. Now, just looking at this, a couple of things should become quite obvious. The first thing is that this is not really high level, and you have to know a lot about cryptography. So you don't really have an API where you can say file encryptor dot encrypt and then pass some file object or some byte array, I don't know. You really have to go down to the wire and create your own cryptographic key and then perform an actual encryption. Then secondly, you have to know how these API actually work. For instance, here these these string parameters here receive the algorithm that should be used for encryption. Now you have to know which algorithms are being supported to be able to pass the correct one to the call here. And on top of that, some of these supported algorithms that you see here in this bubble are actually insecure, like DS should never be used, but it is still supported by the API. So again, you not only have to know which algorithms are being supported, you have to know which of those that are supported are secure to use in your specific context. And then we could go to another example, like here you have to select a supported key size, and depending on the algorithm that you select here, different key sizes are being supported here. Like for AES, that is 128, and 192, and 256. But for other algorithms, these key sizes would be different. Now there are lots of other stuff. There's lots of other stuff that I could point to. One last thing I would like to show you is the number of overloads that this simple cipher init method here has. So these are 9 methods, if I counted correctly. And the first time I used this API, I had no idea which one I was supposed to call. And I decided to go with this one here because it had only 2 parameters and I already had a key. But in the end, it turned out that was wrong, and my program just failed with an exception. So it is not easy to understand these APIs, and it is not easy to use them. By the way, this code here, as straightforward as it may look now, is actually insecure, for a reason we tell you later. And this is really where CogniCrypt comes into play, because we want to help developers by means of an Eclipse plugin, CogniCrypt, and this plugin should help developers use these APIs correctly. And CogniCrypt does so in 2 ways. At first, it has a code generation, and second, it also comes with the code analysis. Now let's first look at the code generation. So when you launch the code generator, you get to this window here, and you first have to select a cryptographic task. So a cryptographic task is basically a programming task that involves cryptography, like data encryption, communication over secure channels, securely archiving files, and so on. Then CogniCrypt asks you a bunch of questions that will help it to configure the code that it will generate for you in the background, We aim to make these questions as understandable as possible to people without or with little cryptography knowledge, but of course we didn't really get around all sorts of cryptography terminology. Then once you've answered all these questions, you get to the solution selection. Here, CogniCrypt offers you a bunch of solutions for your problem, for this cryptographic task, and even recommends one to you, but you can also check out the other ones if you are interested. And then finally, when you selected your solution, CogniCrypt will generate the code. So now let's look at the artifacts that we're using to make this work. We mainly have 3 artifacts. The first one are the task descriptions as JSON files. Here we are storing stuff like the questions that will be asked, the answers, as well as the impact of each answer. So for instance, which statement will be generated when this answer is chosen, or which security parameter is set how, depending on the answer for a particular question. The second thing we have is an algorithm model in the variability modeling language Clother. Here we are encoding basically domain knowledge, like what are the supported algorithms, what are the supported key sizes for each algorithm, how can these be combined, and so on and so forth. And finally, we have code templates in XSL. So here we are basically, we have basically already implemented generic solutions to all of these cryptographic tasks. And at the end, when the user has selected their solution of choice, we are just performing an XSL transformation to insert the solution into the code. And this code that will then be generated for the user. Before we move on, let's now have a short look at how this actually works. So this is the screen that I mentioned. Here you have to select your cryptographic task. As I said, like establish a secure connection or securely archiving files. Once you have selected one task, you also get a short description, so you understand a bit better what this task is actually doing. When you hit next, CogniCrypt will ask you these questions. Again, these are mainly to help CogniCrypt to configure the code that it will generate for you. One such question, even without the graphic error, is what type of data do you wish to encrypt? The default answer is byte array, but we're just choosing string. And then finally we hit next. And here we are at this solution recommendation screen where CogniCrypt says, okay, I've come up with this solution for your problem. And if you want to check out the other ones, you can just uncheck this box here. But in this case, we're just hitting finish. That's weird. Okay, usually you get 2 kinds of code. One is this template usage method that you can't see here right now. This basically tells you how you should use the implementation that CogniCrypt generated for you. The other part that CogniCrypt generates is the actual encryption, like in this case an encrypt and a decrypt method that, for instance, uses this cipher API to implement an encryption. So now that we've seen how the code generator works, let's move on to the code analysis. The code analysis, of course, assumes that you already have some source code, either because you generated it with CogniCrypt or you wrote it yourself, but there has to be some code that the analysis can analyze, obviously. Then you perform some code changes because you want to refactor it or add a new feature or whatnot. And then the code analysis will try to guide you towards a secure usage of these APIs. So the usual use case is you're in your editor and you're editing something. As I said, you may add a new feature or something. And then you hit save. And then the static analysis automatically runs. And for each misuse it finds, it will generate standard Eclipse error markers in your Eclipse. Again, let's have a brief look at a demo. Here we again try to implement some encryption with a field that's telling us the algorithm. In this case, it's AES. And now we just need the 3 cipher statements that we've seen earlier already. Here we get instance call, and we're using the algorithm that is defined here as a field. And then come the other 2, and then we hit save. And this error marker here appears. And it tells us that this parameter is actually wrong. And this is the case because this method here is not just expecting an algorithm, but instead a transformation. And this transformation not only includes an algorithm, but also a padding scheme and a mode of operation. And if you don't pass those, the configuration or the transformation that is used is insecure. And that's why CogniCrypt generated this error message. And now we fixed this basically in this field above here, and we saved again, and now the error marker has disappeared. So currently, CogniCrypt supports 3 kinds of error types, and what these types are and how these work, Johannes is going to explain to you.
Thank you very much, Stefan. So I'm going to speak about the error types that CogniCrypt at the moment supports in the static analysis. There are 3 different error types. The first one is insecure parameters, which we essentially just saw earlier. Then the incorrect usage pattern, that you have to use certain objects in a certain way. And then the last one is insecure class composition, when you have to use different objects and you have to pass them around in a certain way. So let's start with the first error type, the insecure parameters. So we just saw this cipher get instance call with the string parameter as argument. And as Stefan told us, so we have to supply the algorithm, the block mode, and the padding scheme to it. And if you don't do it correctly, CogniCrypt will output an error marker. And so the first string that you see here misses the block mode. So it's just supplying AES is incorrect in most of the cases. And then you could start supplying this block mode, and you start using ECB, which is also in combination with AES insecure. So instead, what you should do is supply this AES/CBC. So that's the first error marker that CogniCrypt warns you about, this insecure parameters. The second error type is about incorrect usage patterns of objects. Here I have a little example of a signature object that you can use. You can instantiate it with this getInstance call, and then you might call init sign, supply it with some private key, and then you call sign to finally compute a signature. In that case, CogniCrypt will warn you that you missed some specific method call to actually supply some data. To explain that in more detail, I want to show you what actually the analysis assumes. So it assumes, or this signature object has certain states. You construct it with this getInstance call, then you supply it with some private key via the call to init sign. And the next thing is you should call update. And with this update call, you plug in the data, or you supply the data to the signature object. Then you can either do another call to update, which adds additional data, and eventually you have to use the sign call to compute the signature object, to compute the signature. So in the code example, what we just saw, the object was constructed, it was supplied with the correct private key, and then the developer just calls sign. So in that case, we want to warn the user that he should have called update at that point. Then, this was the second error type. The third error type is insecure class composition. And again, I want to start with a usage of a signature object because it's easiest to explain on that example. So assume the user constructed some signature object, then he calls init sign, update, and sign in the correct order on the signature object. But there's still something that can go wrong. He might have supplied an incorrect or insecurely generated private key, for example, with an insecure key length. What that means is that because the private key is insecure, then suddenly also the whole signature process becomes insecure. And that's the third error type that CogniCrypt will warn you about. So I've spoken about that CogniCrypt generates these error markers. The question is, how do we specify these error markers? So it's we don't hard-code all these rules into CogniCrypt, but instead we designed a domain-specific language that we call CrySL. And with this domain-specific language, you're able to specify the usage pattern of all these objects, and we applied it to crypto here. So the domain-specific language is implemented on top of Xtext, so you can use an Xtext editor to edit the rules. And I walked you through how you could write a rule in CrySL. So CrySL has a rule for each object type. So you specify, for example, for the signature class, you start writing a rule in CrySL, and the first thing is you have to supply the type that you want to actually specify. The second thing is you want to tell the specification that there are some object that this signature object interacts with. For example, it supplies some data, it will return some signed data, or it uses the private key, or an algorithm that the signature uses. The next block of a CrySL rule contains the events. In the events, you basically select the method that you want to later on use, and you group them into what we call aggregates. So, for example, you select all these getInstance methods and their overloads and group them in one, what we call aggregate here. You group, so these are labeled, so you group G1 and G2 into that label getInstance. And this was the first part of a CrySL rule. And on the second part, that's where all these error markers come in. On the second part, you have a block called constraints. In the constraints block, you can specify that algorithm, for example, must be in the set of these strings. So you have a whitelist approach telling you these are the correct strings that you can supply. If it's not the case, you will receive one of these insecure parameter error markers. Then the CrySL rule has an order block. In the order block, you essentially specify the state machine, the finite state machine that we just saw earlier, in form of a regular expression, similar syntax. So here on the order block, you see that you have to call getInstance, then you have to call any of the init signs method, then you can call update. This plus means you can also call it multiple times, and eventually you have to call the sign, any of the sign method. And that's also where these aggregate come into again. So you define getInstance as all these methods here, and then you can use it in the order block again. Then the last block is a requires block, which essentially will generate these error markers of the insecure class composition. So you have that's a bit more complex to explain. You essentially have predicates that the signature object requires. It requires that the private key that you have is generated correctly, and that's specified in the rule to key pair. So once the key pair was used correctly, it will ensure a predicate called generated private key on the key object, and then you can basically, in the signature rule, you can require this predicate. And that's how these objects interact with each other. And if this required predicate is there, then you won't get an error marker at that point. So that was the specification for the CrySL language, and we specified a total of 23 classes of the Java cryptographic architecture, the JCA, which is the main API for crypto, which is included in the Java runtime. And we specified these 23 classes in a way that we cover most of the parts that you generally require when you do cryptographic tasks. For example, encryption and decryption, signing and verification, if you want to generate a key, or if you want to hash or make any data. So we've specified all these classes, and these are all included in the Eclipse plugin CogniCrypt, and it will check automatically your usages against it. A part of these integration into Eclipse, we are also able to run the static analysis outside of Eclipse, and that's what we did in one study that we just recently performed. And instead of running the static analysis on software in the IDE, we run it on the Maven central repository. The Maven central repository, for those of you who don't know, it's a main repository which contains over 2.7 million software artifacts, and you can easily include all these artifacts within your software with Maven. What we've done is we run the static analysis on all the latest versions of the software artifacts contained in Maven Central, and we unfortunately found out that a high percentage, over 73% of the software artifacts that use these crypto APIs use them in an insecure manner. There's one finding that I want to highlight. to you in particular, and also motivated us to for the title of this talk. And this is a real world application which we scanned, and this is we just copied it into Eclipse and run the analysis again to demonstrate what's the point here. And the problem in the software was that there's a call to keystore.load, and this keystore.load function requires a password as a character array as input. And it does so for a good reason. And in this software, the developer just used a string and transformed the string into a character array. So the password is of type string, which is a bad thing to do in general concerning security. But that's not the point I want to make here. The thing is, in this software, CogniCrypt even found that this string is actually hard-coded into the software. So I'm going to play this video now, and what we're going to do is we uncomment this call, and then CogniCrypt will run the static analysis, scans it, and you see an error marker here. And we now see that it tells us the second parameter must not be changed. And what that means is we now go back to find the definition of our password actually, and we browse the code just backward where it came from. And you see here it's quite hidden in some methods. We are here in the get trust store password method, and it's the return value. Then it's the get key store password method, and eventually we found this hard-coded password here. So under some certain circumstances, the password that was applied to this key store load function, was actually changed. That's actually why we call this talk. If you forgot to change it, CogniCrypt knows it. So to come back to the beginning of our talk, where Stefan motivated that there is a high percentage of misuses of crypto APIs, we unfortunately have to add here that also on the Maven central repository, we found that there are many software artifacts misusing cryptography. We hope that with the Eclipse plugin and CogniCrypt, people are able to implement software in a more secure manner, and we hope that we can help and reduce these numbers. And we do that in two ways. First way was that we generate the code with this wizard where you can generate the code in a secure manner. And the second one is if you change your code, we run this static code analysis and constantly warn the developer instantaneously about problems you might have with this code. That way we hope that we can support software developers to implement software in a secure way. So all this is available at our project website, CogniCrypt.org, where you can check out the code, the rules, and so we are about to move this project to the Eclipse Foundation. So at the moment it's on GitHub. And if you have any further questions, feel free to contact us. And yeah, thank you very much. We hope that you like this talk, and if you do so, you might want to evaluate it as well. Thank you very much.
So the code that you generated, did you have some reviews about that by crypto experts? I mean, if I use CryptoCrypt, I need to trust you. I don't know if you're crypto experts, or is there any more work on that?
The tool is being developed as part of a collaborative research center. No crossing. There was a logo of that on the first slide. And this collaborative research center, there are like 70 different cryptographers who are working on new kinds of cryptography, and we basically worked with them to come up with these code snippets that we produce here.
Why did you choose to make code generation instead of a library with a simple API wrapping all of the complex code? What's the benefit of code generation?
One issue is that the JCA is just so common that it would take years of other people adopting our new API. So it was just easier to to basically, I mean, what we're doing is basically generate some wrapper code around the API, and by that we are already producing a new de facto API, right? And we thought this would be easier than try to compete with the API that is officially being published by Oracle, the maintainers of Java. That's more or less the reason.
Yeah. Is this only for Java?
Currently, yes. We're in the middle of porting this to C++ as well, but this will probably take another few months at least.
Okay. And I have a second question. This works only with JDK embedded library, or does it work with external libraries like CrySL, for example?
That's another thing we're currently looking into, but again, this will also take another few months probably. We have to, we're currently trying to explore several different contexts. One is other crypto libraries, another one is other programming languages, the third one is non-cryptographic libraries, then the fourth one is analyses that are not static, like dynamic checkers, for instance. We're currently branching out in all of these directions, but it will take another few months to get really good results, I would say.
So the CrySL DSL, do you have an interpret to actually run the static analysis, or do you generate code for existing static analysis tools like binders or check styles?
So we actually have a compiler for that, or what we say, it's a compiler to static analysis. So you take these CrySL rules and then CrySL rules, and then you basically static analysis is generated. So it's not based on find bugs. It's based on Suit, which is a big static code analysis framework, which we also maintain. And so we build our analysis on top of Suit.
Just to be sure that I understood correctly, if I try to use old unsafe cryptography algorithm, I risk a lot in this case?
Probably. It depends on the CrySL rule. I mean, we try to make sure that our CrySL rules forbid all kinds of usages of outdated algorithms, but it depends on the quality of the rule if you get a warning for a particular misuse.
So we really did our best to make sure that these rules cover the standards. So we checked them against with a crypto expert, and we read the documentation of these APIs really carefully. I mean, clearly, that's the best we can do.
One last question. Do you take into account the policy of the JDK for security, for example, for key lengths? I cannot use big key lengths for if I don't upgrade the security policy of the JDK.
That actually has recently been changed. They now switch to the unlimited policy by default. But that's
In which version?
Oh, I don't know. I think it came out mid of January or early February. Definitely in one of the Java 8 versions.
Okay. Thank you very much.